Next up, we've got the cardioids. Kind of a weird word, cardioid, but it'll make sense when we start to look at some of the pictures. So a cardioid is a special case. If you look at the equations again, you'll notice that these equations are the exact same equation, but a cardioid is a specific type of limaçon. So this is a limaçon. It's just a specific type, and that's the situation where A and B are the same number. So we still have the same old stuff. So we can highlight this again. We have cosine will be on the x-axis. Sine will be on the y-axis. We're still going to have a big loop, a little loop, other intercepts, and then we're going to decide where it reflects. So let's start to look at some of the characteristics of a limaçon and try to figure out some patterns from the equation, these situations. So let's go over to, sorry, did I say limaçon? I meant cardioid. So let's do this one on Desmos. So we've done a lot on our calc so far, so I'm going to 3 minus 3 sine theta is what I'm going to remember. Okay, so we had 3 minus 3 sine of theta. All right, so you can see that here's our limaçon again. Characteristics we already talked about. If that's a sine, it's going to be on the y-axis. Let's change that to a cosine. Notice it's now on the x-axis. Let's change the minus to a plus. Minus to a plus puts it on the x-axis, but the positive side. And now I'll change this to a sine. All right, going back to the other characteristics, we're talking about a big loop and we're talking about a little loop. If you look at our big loop, it stretches to 6. If you look at our little loop, it's at a 0. So that kind of fits. If you go back to your limaçon table, the big loop is found by adding B and A together. 3 plus 3 is 6. And then the little loop is found by subtracting B and A. So 3 minus 3 ends up being 0. So it makes sense that this still is a limaçon, but it's just a special case of a limaçon. Our intercepts, 3, 1, 2, 3, 1, 2, 3. Yeah, let's change a little bit just to make sure that's true. We already changed all the sines and cosines. So if I change it to a 2 and a 2, remember these numbers have to be the same for you to be a cardioid. And so we go over to 2. Our other intercept is at 2. Our big loop is at 4. Our little loop is at 0. I can change them to 1 and 1. Same thing. I don't want to go usually bigger than 3 unless I want to change my window. Doesn't quite fit on there. So just to reiterate, why did they call it a cardioid? Well, if you look at this shape, I mean, what does that kind of look like? Probably like a heart. And so if those of you who have taken any sort of health classes or studying to be in the medical field know that that prefix of C-A-R-D, cardiac or something like that, is related to the heart. So this is kind of, I think, where they got it from, is this sort of heart shape. So let's go back to our notes here, and we will fill in some of these details. So we've got a big loop. Our big loop is still B plus A. Our little loop is B minus A, which, by the way, will always become 0 in this scenario because B and A are the same value. My other intercepts are the same as for a regular limaçon. There's at A, and then we also reflect, again, if B is less than 0. So let's try to make a sketch. All right, so I'm going to be on the y-axis. I'm going to be on the negative y-axis. My big loop should be 6, so I'm going to go negative. So always start at 0, 0, 1, 2, 3, 4. What? Nice work. Well, that's annoying. I'll fix that on your notes. 1, 2, 3, 4, 5, 6. My little loop is 0. My other intercept is the 3, so 1, 2, 3. 1, 2, 3. And now I'm going to connect my big loop. And then I'm not going to make a little loop. All right, I'm going to pause, see if you, well, that's not supposed to be there either. So I'll fix this on your notes. That is not supposed to be there. So see, play around with your calc or just do it in your head. See if you can figure out what the equation is for this cardioid, which is the heart shape. Hit pause, give it a try. All right, let's see how you did. So let's see. I've got to have a big loop, 1, 2, 3, 4. I've got to have a little loop of 0, and also my sides are, my other intercepts are 2s, so we know it's going to start with a 2. We're going in the positive direction. They got to get to 4. It's on the x, so it's going to be 2 plus 2 cosine of theta. Okay, now the real fun ones are on the back here. These are called your Rose curves. So let's start off, let's jump right into graphing them. All right, so clear out my old stuff. 5 cosine of 2 theta. What a cool picture, huh? Now you see why they're called Rose curves. So the characteristics of a Rose curve, this is what we call a regular Rose curve. Rose curves have leaves. Each leaf has a certain leaf length. And where that leaf occurs is going to depend on, again, sine and cosine just like before. So watch what happens. Here's my 5 cosine of 2 theta. I'm going to change this to 5 sine of 2 theta. So I don't have a great way to explain this. So I still have 4 leaves. When it's cosine, it'll always, the first leaf will always graph on the x-axis. When it's sine, I don't have a great way to say this, it's not going to be on the x-axis. So my first leaf will always be on the x-axis. My second, if it's a cosine, if it's a sine, it will not be on the y-axis. So our equation is based on 2 things that change besides sine and cosine. The a and the n value. So let's take a look right now. Let's mess with the a value. So this number out front is what we had as 5 before. Let's change this to a 3. See what happens to our rows. What do you get? Oops, I forget. Oh yeah, it is. Oh, I forgot to change. I want to on cosine. It's easier to count. What do you notice? How long is your leaf? 1, 2, 3. Let's go back to the 5. How long is that leaf? 1, 2, 3, 4, 5. I messed up my window. When did that happen? Oh no, okay, it's all right. I forgot I squared it off, didn't I? 1, 2, 3, 4, 5. If I go to window of, if I change that to a 6. So what did we figure out? The leaf length. Leaf length is dependent on whatever A is. And now, how many leaves? Is it always 4? Well, let's kind of mess around here. So I have this, so 6 decided how far it was, so the only other thing is this. So your guess, that 2, if I graph it, it had 4 leaves. So let's take a guess here. How many leaves do you think 3 is going to have? You probably guessed wrong, right? So when it was 2, we had 4 leaves. When it's 3, we have 3 leaves. When n is 4, we have 8 leaves. Now you're probably starting to figure out the pattern. When n is 5, we have 5 leaves. Anybody want to take a guess? How many leaves for 6? You're right, there's 12. All right, so a couple things to point out here. First of all, when you graph the 3 leaves, there are really 6 leaves, but 3 of them are on top of the other leaves. So the 3 leaves are exactly at the same angle as the other 3 leaves. So if you watch real close, it'll highlight, and then it'll highlight a little bit more bold afterward. So there's the first round, and see how it's going through? I don't know, it goes pretty fast. Let's go to 7. Okay, let's go to 9, so it'll really take a while. So up in the corner, see how it's thinking? And it keeps thinking even after the graph has already been drawn. So now the more leaves you make, the less accurate your calculator is going to get. Now if you do this on Desmos, it draws it perfect every single time. Let's just quick go over there. So we had, let's do 6 sine of 9. Woof. Look how nice and pretty those are. We could go as many as you wanted to. 15. Ooh, let's try a 16. That'll be 30. Whoa, how beautiful. So anyway, on our calc, we can get our calculator to draw this nicely, but there's a little bit of a price you have to pay to make that happen. So let's say go back to this one where we have 9 leaves. If I go to my window, this thing called theta step, the smaller you make this value, the more accurate your graph will be. So theta step is kind of like how often it takes a picture. So for instance, if you think of this in terms of time, this is going to start taking a picture at 0 seconds. It's going to take pictures for about 6 seconds, and it's going to take a picture every 0.1 second. So the smaller I make this graph, or sorry, this value, the more accurate my graph is going to be because it's taking more and more and more pictures. So the easy question is, well, why don't we always just make it now? This time we're going to really be able to see this thing graphing again. See, it's still thinking, but those leaves, it's graphing the leaves on top of the other leaves. So you have to really think, is it worthwhile to have a super accurate picture, or do you not want to wait that long? So, you know, the question might be, why not make that something really, really small like this? Well, look at how long. Look at how often your calculator's making a picture. Oh, geez. This one's so much. If this ever happens, just hit the on button and it'll stop whatever you're doing. Let's make it 0.001 instead of, I had 3 zeros in there. So look at how long it's taking a picture. Well, yeah, you're going to have a super accurate graph, but you know, it's going to take you 10 minutes to graph it, and it's going to kill your battery along the way. So just hit the on button. I usually use my theta step as about 0.1 or 0.01. 0.01 usually gives you a decent graph at a decent amount of time. All right, so what's this relationship with the number of leaves? So when we had, when n was 9, there were 9 leaves. When n was 8, there were 16 leaves. When 7 and so on. So you probably have already figured out the pattern, but let's actually put it down here. So if n is even, comma, then how many leaves are there? 2n leaves. I'm going to change colors. If n is odd, comma, then how many leaves? Well, if n is odd, there's n leaves. And I'm going to write a little note just to remind ourselves that it's not quite true the way we said it. There are actually 2n leaves, but the leaves repeat. There are actually 2n leaves, but the leaves repeat on top of themselves, so it only looks like there's half as many. All right, well, I ran out of time here, so I didn't even get through one example here, so I'm going to pause it, and you guys can finish up the rest of, we'll do examples 9 through 12 in another video.